last of the effects that we need to look at is one that I refer to as the orbital effect. And essentially it has to do with what is the hybridization of the atom that bears the negative charge. So let's look at these three hydrocarbons. So we have ethane, we have ethene, and we have ethine, and they're all reacting with water to form the hydronium ion and forming the corresponding conjugate bases. You can see the atom effect is essentially the same in all of the cases because the negative charge is on a carbon. There's no possibility for resonance and there's no stabilization by induction. You might first of all think therefore that the pKa's would be pretty similar, but as it turns out, the pKa for our ethine is actually very low, comparatively speaking, especially for a hydrocarbon. This tells us that this conjugate base right here, even though the atom effect is C negative, even though there's no stabilization by resonance, even though there's no stabilization by induction, that conjugate base is highly stabilized. So why is this? And this has to do with what is the hybridization of the carbon compared to the hybridization of the carbon in the conjugate base at the top. Now, I want to remind you about the different hybridizations, and I've made this sketch about sp3 hybridized, sp2 hybridized, and sp hybridized. And one of the things to keep in mind is, in terms of sp3 hybridization, this occurs when 1s and 3p orbitals come together. Of course, sp2 is 1s and 2p's, and then finally sp hybridization has to do with making a hybrid of 1s and 1p orbital. One of the things that we say about the difference between sp3 through to sp is that going this way, there's an increase in s character of the orbital. As you know, an s orbital is closer to the nucleus, and it feels the attraction of the proton in the nucleus more than electrons that would be found in p orbitals. So one of the arguments is that the sp orbital is of lower energy as it is closer to the nucleus. So considering the key questions that are given on this page, the first question asks, construct a statement concerning the relative acidity and the hybridization on the carbon atom. So I'm going to show this on the next slide. So we first of all say the conjugate base that has the greater S character will correspond to a greater acidity of the proton of that atom. So the greater the S character, the greater will be the acidity of the proton on that atom. And then an argument might be the following. The greater the S character, the more stabilized are the electrons on the negatively charged conjugate base. And one of the arguments is that presumably the electrons in sp orbitals are in a lower energy state as they are closer to the nucleus than electrons, let's say, in sp3 hybrid orbitals. I've also seen the argument used that the greater the S character, the more electronegative the atom becomes. People sometimes incorporate the other concept of electronegativity. So if the sp hybrid orbitals were more electronegative, again, a negative charge would be more stabilized. In my mind, some of this feels a little bit like hand-waving arguments, and I'm not so concerned about you being able to justify why an sp hybrid orbital is more stabilized, but I would like you to be aware of the trends, because the fact that our ethine has a pKa of close to 25 makes that a pretty acidic hydrocarbon, and it starts to get into the range of other groups that have similar acidity, but yet the negative charge of the conjugate bases are on other atoms like nitrogens and oxygens. So this is a pretty unique and important situation. As a little bit of practice, let's take a look at this key question number 6, where I'm asking you to identify the most acidic proton in each of these compounds. Now, maybe to help you get started, I'd like to highlight the different kinds of protons that are present. So in A, we have a proton on the end here. We have protons off of the CH3 groups. I'm going to write 1 as a representative proton. And again, we have protons off of the CH3 groups, and we have protons off of this carbon-carbon double bond. In the case of molecule B, we have protons off of a CH3 group, and we have protons off of this carbon making the triple bond. And then finally, in this last molecule, we have these hydrogens. So I encourage you to pause the video and consider circling in each of these molecules which proton would be the most acidic. And by the way, when we start to do this, what we're doing then is actually deciding if we apply a base to these molecules, what's going to happen next? Which proton would be removed? So for A, I hope you appreciate that all of the conjugate bases that would result would have a C negative atom effect. None of the negative charges would have stabilization by resonance. None of them would have stabilization by induction. But when this proton comes off, its conjugate base would have stabilization in a sense by the orbital effect, as the carbon involved would be sp hybridized. In example B, again, it would be this proton that would come off most easily, as again, its conjugate base, negative charge, would be most stabilized because the carbon would be sp hybridized. And then in C, actually I just realized I should have mentioned that there are protons coming off, of course, the methyl groups here. And so, of course, I didn't give you much choice, but hopefully you realize that it's actually this proton or this proton, because they're equivalent, that would be most acidic compared to the hydrogens off of the CH3 group. To end this video, I'd like to summarize some of the things that we've been discussing in the Chem Activity number 14, parts 1 and 2, and I'd like to do one last example. So we've introduced the idea that there are 4 factors that can stabilize a negative charge, and in particular this is important, of negatively charged conjugate bases. So there's the atom effect, on which atom is the charge, and the idea is that you compare electronegativity for atoms in the same row, in other words, the same size atoms, and what is the size of the atoms for atoms up and down a column in the periodic table. We also look at resonance. Is there any opportunity for stabilization by resonance and thereby delocalizing the negative charge? And perhaps you're starting to recognize when you're thinking about resonance that in some fashion it will involve a p orbital. Is there any stabilization by induction, that is the pulling of electron density along sigma bonds? And finally, is there any stabilization by the orbital effect? In other words, the negative charge found on an sp2 hybridized atom or an sp hybridized atom. Now, in terms of how these different factors are summarized, we can abbreviate them as AREO, and hopefully that's an easy way to remember them. The other thing is, it's important to actually consider these in hierarchy. So this is why at the top here I mention in order of priority. So as it turns out, for the most part, the atom effect is, in fact, the most important effect. Then consider whether or not there's any resonance. Then consider whether there's any inductive effect. And then finally, we consider the orbital effect. Now, I'll be running through an example right now, but we'll do several in our live sessions so that you can see that indeed the hierarchy works for many times. And I'll show you a couple of examples where the hierarchy breaks down. I think it would be difficult to look at it as structure, and if you had to decide which is the most acidic proton, and if you didn't have the hierarchy, you might jump right away to looking at the orbital effect, and it might lead you to the wrong conclusion. So I like the fact that we have these 4 factors, and there is a place to start. What is the atom effect? In the key question number 7, I present this chart, and hopefully you're already starting to feel familiar with the chart. Now note, in your course pack, actually the question is presented as just a regular kind of question, and this is found on page 126. But if you look a little bit further, I took the same structures that are in the key question number 7, and I organized them into this chart. So this chart is found on page 127. Again, I'd really like to train you in being able to use the AREO analysis template. So the idea here is, essentially, I'm asking you to compare 3 different protons for their relative acidity. So the 3 protons are the proton that, let's say, is on that oxygen, the proton that's on the carbon right next to the alcohol group, and the proton that's found on the carbon that's right next to the fluoro group. Of course, we have to draw the conjugate base, and we should also identify the protons that we're talking about. So I'm going to go ahead and draw the conjugate bases, as I hope you will too, and then we'll do the analysis. So I have my 3 conjugate bases, and now I'm going to start to fill out the chart. So for conjugate base number 1, I have a negative charge on an oxygen. Conjugate base number 2, I have a negative charge on a carbon, and same thing for conjugate base 3. I then consider resonance, and as it turns out, none of these conjugate bases have an opportunity for resonance. So I put X's there. Next, I consider the possibility of stabilization by induction. Now, looking at the first conjugate base, there is, of course, some stability by induction as that negative charge gets pulled along the sigma bonds towards the fluorine. So I'm going to put 1 tick mark for that. In looking at conjugate base number 2, we have a negative charge right adjacent to an oxygen. And I know an oxygen is pretty electronegative. And also, that negative charge is being affected by the chloro group as well. So I might put 2 tick marks to indicate that indeed there's a greater stabilization by induction. And in a similar way, we've got a negative charge on a carbon over here, but it's right next to the fluoro group, and electron density will be pulled towards the oxygen as well by the inductive effect. I might actually put 3 tick marks here, because again, that negative charge is right next to the fluoro group. This is not meant to be terribly quantitative, but it gives us a rough estimate of what's going on here. Finally, all of the atoms that bear the negative charge would be sp3 hybridized, and therefore there's no difference between them. Now let's construct an explanation. And just as a heads up, sometimes in my explanation, if the orbital effect is in a sense insignificant in that all the atoms have the same orbital effect, it doesn't cause any difference, in order to keep my explanation a little shorter, I will sometimes not include the fact that, the orbital effect is the same. But certainly by completing the chart here and writing sp3 in each of these cases, I have indicated that. So here's my concluding statement. So I make the statement that although conjugate bases 2 and 3 have good stabilization by induction, and the implication there is that it's better than the stabilization by induction for conjugate base 1, I would argue that conjugate base 1 is more stable because it has a better atom effect. Therefore, conjugate acid 1 is the stronger acid. Now note again, if you didn't have the hierarchy of looking at the atom effect first, you might have actually thought that the conjugate base 3 is the most stabilized because the negative charge is right next to the very electronegative group. So I find it really helpful to first of all consider the hierarchy. Again, there will be times where there'll be exceptions, but you will start to get to know when to anticipate an exception. Or I will give you what the pKa's are, and then you'll be able to, in a sense, tease out the fact that there's an exception at play. So there are a few more examples in this chem activity, and in particular in the key question number 7. I encourage you to go ahead and attempt those, and we will discuss them in our live session.